In the last two problems, we just dealt with processes involving a single gas. For this problem, we will be analyzing a gas mixture undergoing a thermodynamic process. Please read and understand the problem. We are given the volume of the tank in which the gas mixture is contained. The proportions of the individual gases are given in terms of volumetric ratios. The initial pressure and the initial temperature are also given. Now heat is added into the gas mixture. But remember that the gas container is a rigid tank, so we can say that the gas underwent a constant volume heat addition process. Finally, the specific heat ratios of carbon dioxide, nitrogen gas, and oxygen gas are also given. From this information, we must find the final temperature of the gas mixture. To compute for the final temperature, we can use the formula for computing the amount of heat added under constant volume conditions. Remember that we use the equivalent specific heat at constant volume because we have a gas mixture instead of a single gas undergoing constant volume heat addition. From this formula, we isolate the final temperature at the left side of the equation. In this formula, there are two quantities that we do not know the values of: the total mass of the mixture and the equivalent specific heat at constant volume of the mixture. But we can solve for these two quantities using these formulas. However, in the computation of the total mass of the gas mixture, we do not know the value of the mixture gas constant. On the other hand, in the computation of the equivalencies of V, all of the six quantities at the right side of the equation are also unknown. The next slides are dedicated to solving these unknown quantities. To solve for the mixture gas constant, we just use the formula universal gas constant divided by the mixture molecular weight. The molecular weight of the gas mixture can then be found by dividing the mass of the mixture by its corresponding total number of moles. Now, to compute for the number of moles of each individual gas, we use the concept of the Amagat's law, which states that the volumetric ratio of the gas in a mixture is equal to its molar ratio. Therefore, if we set the total number of moles of the mixture to be 1 kilogram mole, we can now find the number of moles of each individual gas in the mixture. With the number of moles of each individual gas already known, we can now compute for the mass of each individual gas by multiplying the number of moles by the respective molecular weights of the gases. Once we have determined the mass of the individual gases, we can now compute for the molecular weight and the gas constant of the mixture. Now, before we move on, remember that we still have to find the mass of the mixture. In the computation of the mixture molecular weight, what we did is to add the masses of the individual gases to get the total mass of the mixture. But remember that this value for this mass of the mixture corresponds to 1 kilogram mole of the mixture. Therefore, the mixture mass that we have just computed, which is equal to 35.6 kilogram mass, is not the actual mass of the mixture inside the tank. This is just the mass of the mixture if we have exactly 1 kilogram mole of the gas mixture inside the tank, which is not the case for our problem, since obviously we are not given the total number of moles of the gas mixture in the first place. Now let's go to solving the actual mass of the gas mixture inside the tank. Using the initial pressure, temperature, and volume given in the problem, together with the mixture gas constant that we have just computed, we will get 2.14 kilogram mass to be the actual mass of the gas mixture inside the tank. Now that we have solved the mass of the mixture, let's solve for the equivalent specific heat at constant volume of the gas. To compute for the specific heat at constant volume of each individual gas, we just divide the gas constant by the specific heat ratio of the gas minus 1. Since we are not given the individual gas constant, we write the individual gas constants as the universal gas constant divided by their respective molecular weights. From this formula, we can finally solve for the specific heat at constant volume of each individual gas. Now to find the mass fraction of each individual gas, we are going to convert the volumetric fractions that are given in the problem into mass fraction. To do this, we recall that 1 kilogram mole of the mixture is equivalent to 35.6 kilogram mass. Therefore, if we're going to divide the mass of each individual gas that we have computed a while ago in the computation of the mixture molecular weight by the reference mass of the mixture, then we can now find the corresponding mass fraction of each individual gas. Now that we have found the values of the 6 unknown quantities in the computation of the equivalent specific heat at constant volume of the gas mixture, we can now compute its value, and it's equal to 0.67 kilojoules per kilogram mass Kelvin. Finally, with the mass and the equivalencies of V of the gas mixture already known, we can simply substitute all of the known values in the formula for finding the final temperature of the gas mixture after the constant volume heat addition process. And this is equal to 507.3 Kelvin or 234.3 degrees Celsius.